And thank you for the invitation. So I will be showing a way to compute the fundamental group of a very specific surface. This surface belongs to a famous family, which are called numerical Godot surfaces. So I want to say what I think that is known. So the the algebraic fundamental group of these surfaces, it is known to be one of these 5 possibilities. So 0, Z2, Z3, Z4, and Z5. And Miles Reed, about 40 years ago, I think, proved that the moduli space for the cases Z3, Z4, Z5 is 8-dimensional and irreducible. And the way was to construct explicitly those surfaces. And because of the construction for the cases Z4 and Z5, you can prove that actually the fundamental group is exactly the algebraic fundamental group. Z3 also?
It's not written, but
yeah, it's not written.
It's easy to do by my methods.
So here is a table taken from this survey where you have the Godot surfaces and references to where they were found. So in there it says that it's not computed, the fundamental group for the Z3. In any case, I am interested in the case where the algebraic fundamental group is 0. And in that case, we have essentially 3 types of surfaces. So one of them were constructed by Barlow in 1985. And there you have an explicit 4-dimensional family of simply connected surfaces. So you can prove that they are simply connected. And they all have 4 disjoint -2 curves. Then you have 1994, the Craighero-Gattazzo surface that I'm going to explain very concretely what it is. But it is, well, as I said, it says a quintic with 4 simple singularities. And Dolgachev-Venner proved that the algebraic fundamental group in that case is 0 and that the canonical class was ample. So this is different to the case of Barlow surfaces. And then 2007, you have Lee Park surfaces. I'm going to explain a little bit more about that. And this is an explicit construction, but in the smoothable boundary of the KSV moduli space of this type of surfaces. And they are simply connected. So here you have a table taken from a paper joined with my first master student some time ago. And so the mission for him was to find more examples of Lee and Park type. And here you have them. So the idea is that there I have a surface like this where you have one wall singularity. And what I show there is the minimal resolution of so the Hirschenbruch-John continuous fraction corresponding to the wall singularity. So you know. This is the notation. The wall singularity will be 1 over n squared, 1 n a minus 1. This is my surface X. And the canonical class here is ample. X squares 1. And there you have the minimal resolution. But the smooth model of the smooth minimal model of the minimal resolution. So sometimes, for example, you don't have a rational surface. You might have a Dolgachev to 3. In the case of 4, it's going to be exactly this. And in the next case, you need to blow down to go to the Dolgachev to 3. So in this situation, for example, pi 2, when you get this, you will see something like that, -2, -5. And there will be like a -1 curve touching the -5 twice. You contract, and this is the Dolgachev D23 surface. No, in this case, it's kind of generic. Yeah. And so the thing is that in the boundary, for example, you have for the same singularity 2 different models for the singular surface. The important one for us is the first one that will be used to compute the fundamental group. But this table continues. So you have more singularities. And one thing that we don't know is when these stop. There is a bound, but we don't have explicit bound. And actually, I'm working with Julie on trying to find this explicit bound for the length of this type of singularities. And the case that is very difficult is the rational case. So almost all the time that happens, except that.
They're also elliptic. Much more elliptic. No?
You mean the like Kodaira dimension 1 type of surface? These are rational. I mean the model is rational, but not necessarily comes from an elliptic vibration construction. And here in the boundary, one can prove that you don't find any general type surface. Also, we have in that paper explicit examples with other type of singularities. So these elliptic quotient singularities, where the graph, for example, I explained the notation for the first one, would be like this. And you can also compute fundamental group in that case, and you get simply connected. So this will be the first one. And so we find KSVA surfaces like with those kind of singularities. And also we have some non-normal surfaces on the boundary. But I'm working on that with Genia Tevelev, trying to understand the relation with these normal singularities with mu0 smoothing, like in the talk of Dong-Sul Chin. And so the theorem is that the other example that we have for the algebraic fundamental group is also simply connected, topologically simply connected. So now I'm going to explain the method. So first I would like to explain because we use the method to compute the fundamental group from the boundary. And for the case that I care about, which is the simplest, the quarter 1-1 singularity. So say that we have a surface X with a quarter 1-1 singularity. And we have a Q-Gorenstein smoothing of this. So the way it goes, the computation of the fundamental group, is Van Kampen. For the simplest case, where you take two open sets, so one of them is a neighborhood of the singularity, then the boundary here is the link of the singularity. And so there are two steps. The first one, we do Van Kampen for the surface X, and then here you have these, so X minus, I put the singularity, but it's a neighborhood of the singularity, then free with pi 1 of the neighborhood, but this is 0, and this is over, then the loop, a loop around this link, but you generate, so you find the smallest normal subgroup that in this group that contains the generated by the loop. So here it will be like a loop. So the idea is the following then: if you can prove that in the complement of this singularity, this loop is actually trivial, then we have that the fundamental group of X is the fundamental group of its complement. And moreover, say that I consider an X so that this fundamental group is trivial. Then I have that fundamental group trivial. And then I do Van Kampen here in the smoothing. So here you will have the link, and in here you will have the mean nullifier. And then this is XT. So pi 1 XT will be the pi 1. So this would be exactly this thing. So let me put maybe something like this. The Milnor over that. But in here, what happens is that this is 0. And so you have to quotient in here, but this generate that group. So this would be 0. And And that is the way you compute this fundamental group. Now, how you realize that this loop is actually trivial in this complement? Then you use, so you have to find a situation like this. Let me take the minimum resolution. Here you have the -4. And say you can find a P1 that is intersecting transversally this -1, this -4 curve.
Actually, it suffices a rational curve.
A rational curve? Yeah, this rational curve.
Just go to the normalization, contract it there, and take the image.
Yeah, so that is what I said, a rational curve. This is the minimal resolution of this curve. So I have that, but then I need a rational curve intersecting at one point.
But I mean, it doesn't need to be smooth, the rational curve.
Yeah, it doesn't need to be smooth, right? Yeah, that is true. And then, so the idea is that you have this loop, but you take this P1 and you contract it. It disappears. And this is what we are going to use. So we need, at the end, okay, I will explain the plan later, but at the end we would like to have a situation like that. So a P1 transversal at one point to this -4 rational curve. So this is the way it goes. Now I would like to explain an example how this situation appears. So say that we take a rational elliptic surface with sections that has a configuration of singular fibers like this. So I0 star and how many? Now I forgot. Let me see. 5, 6, 6. I1s. This would be the situation. This is my I0 star. And actually from these 6 I need 2. And then say that we have 2 sections like this. So this is Lie part construction of a specific surface. Now I will do some blow-ups. So let me see. And here we need to blow up also in a section like that. These are blow-ups. So here in the node you take two blow-ups, and then I blow up here and here, and also here. Sorry about that. So this becomes -4, -3, -3, because they are -2 curves in here, and then you have -2, -2. Here you have -2, -2, and minus, so whatever it has to be, 6. So from that situation, so this is the certain blow up of this situation. Now I contract the -4 curve, and the other 2 wall chains. So you get something like this. And actually what happens, so this surface has k squared equal to 1, but k of x is nef. It's not ample because there is a 0 curve, and that 0 curve is should be connecting these 2 chains right here. So this would be the 0 curve. So after you contract this curve, say that this is the curve, you will have this lemon-shaped surface with a quarter 1 singularity and the other one that I showed there. So that one, the 1/2 times 7 squared, etc. And also in this case, okay, I forgot. And also in this case, I will consider this -2, one of these 2 -2 curves. That's going to be there. So then, I'm explaining this because it's kind of important what we do at the end. So I will repeat the situation here. And this is the other one. And then what you do is to smooth one of the singularities. So you can smooth this one or this other one. If you do that, you can prove that this is rational again, the surface. And if you do the other one, you can prove that this is the minimal resolution is a situation of a Dolgachet 2-3 surface. And you can do it keeping the -2 curve. You can prove that you can keep that. So this would be a D23. And using Van Kampen, if you like twice, you can do it. I mean, maybe you can do it here and then go to the inside here. Here you will have the Godot simply connected surface. You can do it from here or you can do it from here. So then what would be the idea? Oh, but first let me explain this. So if you have a situation like I explained, that you have an X with a quarter 1-1 singularity and the canonical class is Nef and K squared is 1, then the minimal resolution has to be an elliptic fibration with codec dimension 1. And that is not hard to prove. And moreover, if you add that the algebraic fundamental group is 0, then it has to be a Dolgachet 2-3 surface. So the idea would be you have the modular space of, and here is the Craighero-Gattazzo. We would like to degenerate to this boundary, and where you have a quarter 1-1 singularity. We will use that the fundamental group, the algebraic fundamental group of this is trivial, and so this has to have algebraic fundamental group trivial, but actually it will be a Dolgachet surface, so it's simply connected. Then try to get a -2 curve, and then go and prove that this one has to be simply connected going to the inside. This is a Q-Gorenstein degeneration to a surface like that. But so the idea is to go to this simple situation, but the big problem is how to find a degeneration for this very special surface. It's very, very special surface. So now I show the surface. So this is the Craighero-Gattazzo quintic. So very explicit equation where the coefficients are taken from this paper, from Catanese and Pignatelli, multiplied by 49. And so the coefficients live in this set R, where R satisfies this equation. And then this surface has 4 elliptic singularities at those points. You resolve and you get this Craighero-Gattazzo. And there is a picture of it, where you should see the singularities. And so, as I said, the key part is that the coefficients live in this domain. So what we would do is to try to, because I don't know, we couldn't come up with any degeneration of this situation. Maybe the only possibility would be to keep the singularities and change the J invariant, but we didn't know how to do that. So what we did was to jump to some certain characteristic P situation. So let me explain that. So instead of going like this, we just trying to jump to characteristic P, and where we have a degeneration like the one that we want to have, and then try to lift that degenerated fiber to a characteristic 0 situation, and finally prove that there is a smoothing for that situation that joins to this Craighero-Gattazzo surface. And in this situation, in characteristic 0, we will compute the fundamental group, so the fundamental group will be the same, and so it will be trivial. That is what I'm going to explain now. So the first thing is to find the right prime where something good happens, and that was done by an undergrad student of Genia, Boyd.
So the 3 roots are 1 real and 2 are complex.
Yeah, maybe, yeah. Mm.
So which real roots? Any roots?
Hmm?
Oh, okay.
Tentatively as a real root. At least.
Sorry.
So at the beginning, so one can, so this guy Boyd was in charge to find an expression of this equation over some set p numbers, so that at the beginning you have a degenerated situation that we can work with. And he realized that when you take 7, this 3 is simple root of this polynomial, so you can, by using Hensel lemma, you can consider this Craighero-Gattazzo quintic over set 7, and then you have the 7 expansion, and you will find that for 7, the Craighero-Gattazzo quintic becomes a double quartic with a plane. So a situation like this. In characteristic 7. And this is double and a plane. But this is too bad for us. And this is so, okay, let me start to explain, write down the situation. So we will have, actually at the end we will be working not over set 7, but we will be working over the bit vectors of the algebraic closure of that, and this is going to be my R, spec R. And at the beginning, so we have that in characteristic 7, so in characteristic 0, we have this quintic, the Craighero-Gattazzo quintic. Characteristic 7, we have this situation, double 1, and this is my initial family, but you can change it to another family where there is a certain double cover of this situation plus a simultaneous resolution of these singularities, but at the beginning a double cover of the situation where you have in characteristic 7 this quarter 1-1 singularity and 4 elliptic singularities. So the same for the quintic. And then simultaneously we resolve these elliptic singularities to have the first family. So maybe this is Craighero-Gattazzo. And now we have this surface. It's over spec R. So I will describe exactly the minimal resolution of this surface. We call it, because he found it, the Boyd surface. So I guess this would be my S0. This surface is what we denote by S0. I will describe this surface very explicitly in a moment, but I want to continue with the strategy. So this is going to be explicitly described in a moment. And it is a Dolgachet 2-3 surface in the sense that it's codary dimension 1, and there are two multiple fibers of multiplicity 2 and 3, and very specific singular fibers that I will describe. And we have the situation in characteristic 7 that we want. So we will have this -4 curve and a -2 attached that is transversal at one point. But this is characteristic 7.
Well, I mean, I don't understand. You have the generic point is over the generic point there is a Craighero-Gattazzo.
Yeah. And the special point, we have this singular surface with a quarter 1-1 singularity. So what happens is that this singular surface, one can compute obstruction and it actually vanishes. So we can lift the singular surface, the one with this singularity, and there is a -2 curve here, to a surface, an actual Dolgachev surface, to 3 over the complex numbers that has the same singular, that there is a -4 curve and a -2 attached transversally, so that we can contract the -4 and get this surface. So we will have a situation like this. This is family 1, this is going to be family 2 over the same base. So the generic fiber in characteristic 0 would be a Dolgachev surface with a ⅓1 singularity. So they lift the surface and a curve. And in characteristic 7, we have the same situation, where this is coming from the void, from this. So this is exactly the S0. So we have these two families, and then what we do is that to use this no obstruction computation to prove that there is a sort of smooth finite type scheme T over R. So this would be my T. There is like a local moduli for this S0 surface. And this is over R, where we have these two families. So and then, so we have these two families. One can imagine that the generic point is somewhere here, and then one can prove that over the the K is the quotient field of this R. Then we go to algebraic closure, and this situation gives an irreducible curve join this characteristic 0 situation with the Craighero-Gattazzo situation. So this is the complex Dolgachev surface 2-3 after you resolve the ⅓1 singularity. So this is roughly the idea. And now you apply what I did at the beginning, computation of fundamental group of the smoothing, Q-Gorenstein smoothing. And this is a Q-Gorenstein family for this surface. So this curve will give a Q-Gorenstein degeneration of the Craighero-Gattazzo into this singular Dolgachev 2-3 surface. So that is the picture. Well, I'm trying to describe that. And now I want to describe this void surface that is very particular, very special. Okay. So as I said, this void surface is a double cover of P1 cross P1. So here in the picture what you have is P1 cross P1. And then this B1 plus B2 is going to be the branch curve for the double cover. This delta is diagonal, is a certain diagonal, so belongs to 1, 1. That intersects these B1 and B2 in that way. So you have tangencies, and then you cross twice, and then you have the same for the other. And also we have the situation that there are two fibers like this for the two rulings and the other two.
Is the diagonal a part of B1?
No, it's not. And then we have these two fibers where the B1 and B2 are doing what I described there. So something like this, and the opposite for the other one. and the same in the other fiber. So to check what we get in the double cover of this branch along this B1 plus B2, what we do first is to resolve singularities. So we blow up over these points P1, P2, P4, P3, P4 twice. And it happens that what you get is the following. So these 4 will be the first time that you blow up the points Pi, and then there are these sections for the next. And I'm writing this down in this way. I'm drawing this in this way because actually what you get is an elliptic vibration. Where we have a multiple fiber of multiplicity 3 for this I8. And here there are other 2 fibers like that. And then the branch, now if we look at the branching here, it's going to be like this. So say blue. So we have these, and these, and that.
I don't understand. The curve B1 would have genus 4, but it has 2 points of type 2.
Genus 4? No, it has genus 0.
Okay.
Yeah. Genus 0.
It's rational.
It's rational, yes.
But the elliptic curve is B1 plus B2. After you go.
The elliptic curves are going to be, these sections that I didn't draw. So there are sections here. When you pull back that in the double cover, we will have the.
It's this.
Hmm?
I2 is just 2 rational curves meeting in 2 points.
Yes.
Okay. So,
And that will be given by the B1 and B2.
Okay. We didn't see it.
And so and the one important thing is this delta. So let me see if I can draw that. Something like this, like this. So this is a 12th section, so something happens in here. Let me put points. And then you go like this. And then it's tangent, 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 and like that. So when you look at the double cover of this situation, branch on the blue curves, so these are -2, -2, -2, -2, -2, -2. This delta curve will split in 2 -4 curves. And that is how we get the -4. So, well, in the double cover from here, we will get these A1 singularities in these nodes. We resolve, let me resolve that. So this is 2 to 1 plus resolve 2 A1s. And we will have this. So here is B1, B2. Let me call this N1 and 2. And this now is going to be a double fiber for the corresponding elliptic vibration. The pullback of these 2 are going to be like that. And then the pullback of this I8 will have these -1 curves and -4. So we contract. So maybe plus contraction of 4 -1 curves. And we get another I4. And that has multiplicity 3. And this is the Boy surface. Now the yellow curve will split. And so we will have a situation essentially like this. And now let me also jump into this situation where we cross. and we do like this, and like that. So let me see, this would be 3 times 4, 12, and 6 times 2, 12, because this is a 12 section. So it has to, this thing here is a 12 section with self-intersection -4. And you see here is what we wanted. So for example, we can take this -2 curve, so having the situation that we wanted. But now, of course, the problem is that we need to compute this obstruction equal to 0, which is not that easy. But the idea is that the problem of obstruction in here can go to the problem of obstruction of certain configuration in here. Actually, the configuration is the delta plus the B1 and B2. And that can be computed explicitly, long computation, using that this is a blow-up of P1 cross P1. It's an interpretation of the meaning of what we want to compute in here.
Sorry, this does exist in any characteristic or just in characteristic 7?
Characteristic 7.
Just in characteristic 7.
I don't know if just in characteristic 7, but it works in characteristic 7.
Found in characteristic.
Yeah, we found it in.
Why does it does not exist in characteristic 0? This
I would say that, yeah, that maybe one can do a computation to prove that this configuration cannot exist in characteristic 0. I didn't do that, but I don't believe that it exists.
So you found it in characteristic 0.
But then there is a lifting, and I think that what happens is that these points, PIs, move. So we can preserve the singularities in the lifting, the intersection with delta, we can preserve all of that, but I don't think that we can preserve that these two are in one fiber, like in here. I think that they move, they will move. What's happening here? Yeah, I cannot move to the next. Oh, okay, thank you. Okay, so this is what I just did. There you have the curves, and as I said, we compute obstruction in that way. So the key of computation that we need to do to have all of this is this one. So Z is the blow up. I think that is this, but you need to blow up also here, because we want to have the delta and the BIs transversal. We want simple normal crossing. And also we need to blow up here, and here, twice. And then we need to compute that. Okay, so I want to say some things about this situation. So one is that so here is a double cover construction like Campanelli type construction. So you can see this, for example, in P2, trying to keep the 3 points, and then we will have a degree 10 curve, but it's reducible. We have 2 degree 5 ones, where we have 3 points, 2 4-fold points, and a double point. So at the end will be very interesting, I guess, to see, because in the Craighero-Gattazzo surface, Dolgeschew-Werner also described the situation of a Campanelli curve and a double cover. How the double cover degenerates, I don't know. And also to see how a double cover degenerates to acquire these quarter-1-1 singularities. Another point is that in this void surface, we can see 2 genus 2 fibrations given by the rulings, and with 8 very specific type of configuration of very specific singular fibers. So I will draw them somewhere here, maybe. So this is another way or the void, which would be genus 2 fibration. So here the general fiber has genus 2. And then you will see this situation, which is different from. I have to say that also Igor and Werner consider this genus 2 fibration, and where they have different configuration of singular fibers. Here we have this elliptic, and a rational one in between, and twice. And then we have two nodal like this. And these N1 and 2 are crossing like that, forming triple points. And then there are 4 pairs, and where this is elliptic but singular. And we have 2 of them because of the 2 rulings. And now what we did is to, since we have this obstruction computation, we wanted to find a genus 2 fibration that is actually Lefschetz, so in the Dolgachev surface, because this leads to the Dolgachev. And then we need to eliminate this situation of triple points, and we can do it with the computation that we have explicitly. And so we have at the end, on a Dolgachev 2-3 surface, a genus 2 fibration, which is Lefschetz, in the sense that the fibration has reduced nodal fibers only. And I think that in the Craighero-Gattazzo also there is a Lefschetz fibration, genus 2. Okay, so maybe I went too fast, because I think that I don't have anything else.